Hello, my students. This is a video about exponential functions. Today and in so many other series of videos, you will learn more about exponential and logarithmic functions. So this is first video, part one. It's all about exponentials. So we'll explore, we'll learn how exponential function looks like, and hence learn the important vocabulary that you need to know. And also we will learn how a logarithmic function is an inverse of an exponential function. But let's see what we can do best in this video. So this was the worksheet that was given in the class. So let me gather this back. Okay, so I'm going to my pen. Okay, so each spring, the nation's top 64 collegiate basketball teams are invited to play in the NCCA tournament. When a team loses, it is out of the tournament. So he's saying he's starting with 64 teams. So by the end of one round, how many would be left? So if a team wins, if two teams are playing in a tournament and one team wins, the other team loses. So we are looking at 64 teams playing. So by the end of the first round, you'll be left with 32, just half of it, 32 teams left. By the end of second round, you will see 16 teams left. And third round, it will be 8. Fourth round, 4. Fifth round, you have 2. And the last round, the sixth round, you'll have 1 team left. Will there be a value of 0 in the y? No, because it's a constant 1, because no matter how many teams are playing, but then you will be just left with 1 team. How many teams are left after the first round? So these questions are given to motivate you. So how many teams are left in the tournament of the first round? 32. So now we completed this table. How many rounds of games must be played? See how many rounds have been played? There are about 6. So 6 rounds. Now we are going to graph this. So this is my graph here. We'll start with this side. We'll label it as number of rounds. That is my independent variable x here. And on this side, we'll have number of teams left. So we'll start out our graph nice and easy. So 1, 2, 3, 4, so on and so forth. And here we have values from 1 to 64. So I'll conveniently count from 2, 4. I'll take my scale as 2. So each block will be 2 units. 2, 4, 6, my apologies, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. Let's stop here. I know 32 will be somewhere there. So at 0th round, it will be somewhere really at the top. At first round, it will be 32. Even that we can't see within this graph. So let's start out with this second round, just 16. After the second round, there will be 16 left. So this is what we have here. That is 1 point. And then after the third round, you'll have 8 left. So 8 is here. And after fourth round, you'll have 4 left. So here. After fifth round, you'll have 2 left. And after that, you'll have just 1. 1, 1 all over. So our graph, looking at that, if I make a nice curve this way, it'll go here. Will it ever touch the x-axis? No. So we'll talk about that also in a bit. So let's answer these questions for now. So this is our graph. Looking at the graph, is the function linear? It is not a line. It looks like a curve to me. So it is not linear. Not linear. Is this graph quadratic? Well, for a parabola, if there is something coming down, there is something going up also. I don't see that this is a quadratic. So this is not a quadratic because the value stagnates at 1. It's not coming up at all. If the table was extended indefinitely, what would happen to the y value? Y value will remain constant at 1. At 1. So the basketball tournament is an example of an exponential function. So this is a classic example of an exponential function. So how do you write the standard form? It is f of x equals a times b to the x. So a is the initial amount. B is the growth or decay factor. And X is the number of trials or number of rounds in this case. So this is a great introduction to the exponential function. And this is how the standard form looks like. This is the parent function. F of x is equal to b to the x. So this is a growing function. See how it is growing from here and it's going up. This is exponential growth function. And if you see, it has a y-intercept at 1. All right. And 1b is where there is the second point. So the graph rises from left to right, passing through the points 0, 1, and 1b. So as I told you earlier, the b, which is the base, is called the growth factor. It is a growth factor because it's a growing function in this case. Here it is a decay factor because the values are coming down here. So this is like a decay function. So in a growth function, b is always greater than 1. You have to remember that. In a exponential growth function, b is always greater than 1. And in the x-axis, look at the x-axis, this curve never seemingly touches it. So this line, which is closer to a curve, where a curve seemingly looks like it would touch, but it will never intersect or touch this line. This particular line is called an asymptote. So mathematically, how would you say it? An asymptote is a line that a graph approaches more and more closely as x is approaching negative infinity. So this is how an asymptote is defined. In this case, he is saying as x tends to negative infinity because we're going in the left side of the coordinate plane, which is all negative values. In the case of decay, the decay factor lies between 0 and 1. Okay, did you observe that b cannot be negative at all in any case? So the b is representing the decay factor. So the graph is going toward the positive direction, but it stagnates at one constant value, as you have seen in the previous basketball example. So this curve tends to or approaches the x-axis, but never touches it. So that's how you define an asymptote here. Asymptote is a line that the graph approaches more and more closely as x tends to infinity. Okay. You see that 0, 1 is again the y-intercept here, and 1b is another point lying on the graph. So this is how you define the parent function for an exponential function. So let's go to the next slide. So this is how an actual exponential form, a standard form, is defined. So you have y equals a times b to the x, and you have everything defined here. The y-intercept is at 0, a. So a gives the intercept. and b gives the growth or decay. X is the exponent. In most of the cases, it's number of trials or number of rounds. So this is how B is defined. So if you see, B is 1 plus or minus R. So if the growth factor is 1 plus R, there is a percentage increase, R. If it is a decay factor, if it's a decay function, this is 1 minus R. So the initial value A, I've written it down, whatever I just told you. Let's go to the next slide. We'll look at this worksheet and try to complete this. So I'm choosing my X values. Remember, X is always an independent variable, so I choose my values. So -1, 0, 1, 2, 3. These are the values I'm choosing right now. So if you plug in -2 in place of X, so 2 to the power of -2, -2 is 1 over 2 squared, which is 1/4. So this particular value, the y value is 0.25, and hence if you go to 2 to the power of -1, it is half, so this is 0.5. 2 to the power of 0 is 1. Anything to the power of 0 is 1, remember? For if x is 1, it is 2 to the power of 1, which is simply 2. If x is 2, so it is 2 squared, 4. If x is 3, 2 cubed, 8. So these are my tabular values. So I'm going to express this in a graph. So this is like -1 and -2. If these were the x values, the y values were like 0.25, 0.5, and at 1 it is, at 0 it is 1, that is my y-intercept. At 1 it was 2, it was 4 next, 3 was 8. So look how the graph is building on this way. So this is the typical characteristic of an exponential growth function or a decay function. You will see the first few values growing slow, but after a couple of values, it will just shoot up, just goes up. So that is why we call it exponential growth. Now this time it's a decay, so y is half to the power of x. This is also 1 to the power of 2x. Remember that from properties of exponent, this x distributes over both numerator and denominator. So I'll choose -3, -2, -1, 0, 1, 2. So for -3, so this is 1 over 2 to the power of -3, which is 1 over, actually let's bring it up, it's 2 to the +3. So this is a +8. Because when you bring it up, the negative exponent becomes positive. Remember your properties of exponents. That's why they have become handy, especially in these exponential functions. So the next value will be 4, 2, 1, 0.5, 0.25, so on and so forth. So -1, -2, -3. So -3, it was 8. Somewhere here, -2, it was 4, and so on and so forth. The graph will now come this way. Okay, now let's see. Now what is the factor here? What is the growth factor? We are talking about growth because this is exponential growth function. The factor is 2. So we can split it as 1 plus 1. Remember from the previous slide? It was 1 plus or minus r. If it is 1 plus r, it is growth factor. If it is 1 minus r, it's a decay factor. So let's come back. So this is 1 plus 1. So actually, what is the percentage increase? It is 100% increase. In the decay factor here, the decay factor is half. So now again, if you go back, it is 1 minus r. Look at this, 1 minus r. So come back. So this is 1 minus 0.5 is 0.5, isn't it? So that means the percentage decrease was 50%. All right. Now, in the basketball example, an exponential is the basketball example a growth or decay function? What do you guess? It is a decay function. How do you know if an equation models growth? Look at the b value. First of all, as the x values increase, the y values also should be decreasing. That's how you know it is a decay. So let me write, as x tends to infinity, y tends to negative. It's approaching toward the negative values, or whatever is the asymptote. Maybe I'm not right in saying this way. But when you look at the growth, as x approaches infinity, y is also approaching infinity. Maybe I'm right. Okay, anyway, so this is the growth function. But mathematically, how would you represent it? The b will be greater than 1. Here the b is between 0 and 1. Okay, now let's move on. Let's look at this practice. So this is a good practice. Remember, look at A, identify each as modeling exponential growth or decay. So in this particular question, 1500 times 2 to the x is a growth, because look at the growth factor. It is 2. The 2 is a positive, more than 1. It's a whole number, so it's a growth. And what is the b? Identify the initial value, which is 1500. Okay, and c is the growth or decay factor. It is 2 here. And what is the percentage increase or decrease? It is 100%, because 2 is 1 plus 1. So this is the one we are talking about, 100% increase. Let's do one more. We have a decay function here because it's 0.1. It's between 0 and 1. So A, the initial amount is 5.65. Oh, sorry, we have to write. I'm sorry. A is where we have to write it as decay or growth. So it's a decay here. B is the initial amount, 5.65. 0.1 is the decay factor. So 1 minus 0.9 is our 0.1. So 90% is the percentage decrease. Do you get it now? Okay. So let's look at this 10th question in your worksheet. This is a real life situation again. They started the population of the 4 largest cities in the world is in 1994 is this. So suppose these rates continue to grow. What is the equation that models the future growth of each city? So look at this. For Tokyo, this is the initial amount. So that is what, remember, y is equal to a b to the x. A is the initial amount. B is the growth factor. And x is the number of years here, because he says annual growth, so it's number of years. So Tokyo, now this is y equals the initial amount, 26,518,000 is my initial amount. B is the growth factor, so 1.4% is the growth percent. So this is like, let's see, I get this out. 2.4, because 1 plus or minus r, remember that? This will be your equation. This 1 plus or minus. So in this case, it is plus, so 1 plus r. That is the reason why it is 2.4. I'll do, the New York City's population is not growing, actually it's decreasing, because you have 0.3. Oh, no. It is still, I take that back. New York City is still growing, so 16,271,000 is the initial amount. Now it is 1.3 to the x. I'm sure you can fill in these two. Okay guys, this is a small introduction with the worksheet that has been given in the class. I hope you will fill in the worksheet. Your homework is similar to this one. Hopefully in another video I'll talk about the homework also, but this was what is planned for the exponential functions. In a second video, I'm going to talk about graphing exponential and logarithmic functions. Okay, thank you so much.